Okay, precalculus work. Okay, so determine if each function is continuous at the given x values. If not continuous, classify each discontinuity. At x equals -3, just simply substituting in -3, we obtain 9 take 9, which is 0 on the denominator. And it clearly refers to this portion of the graph here. So I would say that for x equals -3, this is an infinite discontinuity. Infinite discontinuity. And for x equals 0, this is a removable discontinuity. Notice that it is actually defined if I were to substitute in x equals 0. It's just that they have excluded it from the domain. For this this is a rational function, by the way. For this piecewise function, f of x is -2 when x is less than or equal to 3, and x take 5 when x is greater than 3. And we have to analyze what's going on at 3. So it's not differentiable at that point right there, but it is continuous. So I believe that I can just say x is f of x is continuous at x equals 3. And now I must check. Okay, that's in agreement. All right. Next, we have the rational function f of x equals x at 1 over x squared at 2x at 2. And we have to investigate its behavior at x equals 3. So just substituting at x equals -3. Substituting in x equals -3, we obtain 9 there, -6 there, and 2 there. And the sum of those is 5 in the denominator. So I believe that it's continuous at that x value. Now, for this rational function here, where we have x squared take 4 in the denominator, substituting in +2 or -2, we obtain 0. But what kind of discontinuity is that? It will be an asymptote. Like I'm trying to visualize it. So it becomes ever more negative. For x equals 2, it becomes ever more negative. And then obviously it's undefined for x equals 2. And then approaching from the right, it becomes ever more positive. And so it's infinite discontinuity for sure. But I want to start understanding the behavior. Infinite discontinuity. And for x equals negative 2, so as I approach from the right, I have a negative number on the numerator and a negative number on the denominator, but they become ever larger but positive. And as I approach from the left, I have a negative number on the numerator and a positive number on the denominator. They become ever larger negative numbers. So it will look like that. And so it's another infinite discontinuity. And I must check. First I will just check and see. Right, okay, so that's essentially different. It always takes forever and ever to load. Desmos, monostream. I'll show you what I mean. There we go. Right. Add x plus 2 over x squared take 4. Right, so here's what we obtain. Okay, so there it doesn't sort of like highlight the whole, but I should have detected that. Anyhow, sort of like too late now, but like how can I think about this? Okay, so like it's mimicking the 1 over x behavior. So it's not going to have 2 of these. So only one of them can be an infinite discontinuity. That's what I need to think about it. So there is a removable discontinuity. Okay. Okay, so this will essentially have the behavior of a linear function, but I want to know what the more precise language of that is in a second. And therefore, I believe that that will be a removable discontinuity. And here, if I just simply substitute in 3, I'm obliged to evaluate this piece of the function. So that's the negative of 9 plus 24 take 16, which is negative 1. Whereas if I put it in here, I get negative 6. So it's gone from negative 6 to negative 1. Like that. That's what my function has done. And as it's negative 2x, it will come down like that. And as it's negative x squared at 8x, it takes 16, it will branch out like that. That's sort of the behavior near this point of 3. And so this is a jump discontinuity. And we must check. Okay, darn it. That's correct there, but this is not a removable discontinuity, it's an infinite discontinuity. Right, okay. X squared of x plus 1. All right, so it actually looks like that. It doesn't imitate a linear. That's wrong. That's the wrong way to think about it. Okay. Of course it won't be. Right. That is an infinite discontinuity. Okay, so this teaches me that I need to investigate the behavior of functions more properly near the points in question. Determine if each function is continuous. If the function is not continuous, find the x-axis location of and classify each discontinuity. So we have a quadratic in the denominator, and therefore if it has any zeros, the entire function will be discontinuous. So to test if it has any zeros at all, we can use the discriminant, which is b squared minus 4ac. So in this case, b equals 2, a equals 2, and c equals 1. And 4 minus 8 is negative 4, and so this sort of like hovers above the x-axis. It has no zeros. And so I believe that this is continuous. And I'll say that as the quadratic in denominator has no real roots. All right, for this situation over here, which is similar, b squared minus 4ac, 36 minus 4 times 1 times 9. And that produces 0. And so it has, I mean, of course I can just see it, but it has like a repeating root at x equals 3. And therefore, I need to investigate the behavior at -3. So at -3, it will simply be undefined. But let's see now. I don't know if this is a valid approach, but I'm going to try -2.9 and then -2.99. -290. -29,900. And then I'll investigate for -3.1 and -3.01. Plus 6 times -3.1. There we obtain -310. And there we obtain -30,100. So as you approach from the right and the left, you tend towards negative infinity. It sort of like dips down like that. So I will say that it's an infinite discontinuity. And now I will check. Okay, correct. Next, the numerator can be factorized into x at 3 times x at 1, and so we're tempted to cancel the x at 3's, but that would remove or delete information about what's valid and not and invalid in the domain. So x equals -3 is clearly of interest. And we must classify that discontinuity, but we must okay, so in this case we can actually think because we can cancel the x at 3 on the top and the bottom, it will behave like x at 1, except at -3 it will have a hole. So that one is a removable discontinuity. And for this one here, we can factorize the denominator into x times x take 4. And so we could cancel the x on the top and the bottom. And then it would appear like 1 over x take 4. And 1 over x take 4 is like the standard hyperbola of 1 over x, but translated 4 units to the right. And so it would be an infinite discontinuity. I believe. But now we must check. Removable discontinuity at x equals -3. Okay, that's true. Removable discontinuity. Okay. All right, so this is pretty appalling. I didn't check for that. It is an infinite discontinuity at x equals 4. But remember at x equals 0. What happens at x equals 0? Well, for the cancelled factor on the top and the bottom, that's where you get the removable discontinuity, I believe. Okay. Now, trying this one. Piecewise function x at 4 for x is less than or equal to -2, and -2x take 11 for x is greater than -2. So the linears are defined everywhere. It will be -2. That's of interest. Here, f of -2 equals 2. And here, f of -2, though it doesn't call this branch of the function, would evaluate to -7. So that is a jump discontinuity. At that point, at that input there. The points of interest are x equals 0 and x equals -3. And at x equals 0, it's clearly undefined, right? But what's the behavior at that point? we get 23 for 0.1. We get 232 for 0.01. Negative 23. Negative 200. So they're approaching from opposite sides. So it's an infinite discontinuity. Approach from the right. Negative 14-ish. Okay, getting larger negative numbers. And now approach from the left. You get larger positive numbers, so it's an infinite discontinuity as well. And we check. Okay, that's correct. Find the intervals on which each function is continuous. All right. I believe that it will be continuous from negative infinity to well, I guess to 4. Like that. We'll see in a second. It's continuous from negative infinity up to 3. And then 3 onwards. Okay, but I must check. Right, okay, so when you have a removable discontinuity, you clearly don't include the end values in either case. But over here, where you have a jump discontinuity, you would because it is defined for that value there. All right. All right, for this function here, so we can rationalize the denominator. Like that. And so it will mimic the hyperbola. It's just that the points of the values of 1 and 3 are of interest. So, like, I know that it'll be intervals like from infinity to 1, and then 1 to 3, and then 3 to infinity. Somehow, those will be open. But what happens for 1 and 3 themselves? Well, we can't input 1 and 3, so you must not include them at all. So I think that it's continuous for the union of these 3 open intervals here. As for this one, I think that this is continuous for the entire real number line. Or if you prefer, negative infinity to positive infinity. But now we must check. Okay, that's correct. Good. And here, this is continuous for negative infinity to positive infinity, or the real number line. Now we have a quadratic in the denominator, and it's a factorizable quadratic. It's factorizable into x take 2 times x take 1. And so the entire function is mimicking the hyperbola, the standard hyperbola xy equals 1, but translated to the right by 1. So the points of interest are 1 and 2. 1 and 2. So we go negative infinity, 1, 2, like that. It's not defined when you input 1 and 2, like that. But we must check. That's correct. Okay. Factorizable. X take 1 in the numerator. X open brackets x take 1 in the denominator. Mimicking the hyperbola. Entire function undefined for x equals 0 and 1. So negative infinity, 0, 0 to 1, and 1 to infinity. I believe it's like that. Denominator can be factorized into x take 3 all squared. So that's a repeated root. So it's undefined at x equals 3. I'm not sure. Can I sort of do this? Negative infinity to 3 unioned with 3 to positive infinity. But we must check. Okay, that's valid. Write a function that has an infinite discontinuity at x equals 100. Okay, so we can do the regular hyperbola, but translate it to the right by 100 units. So just do that. Write a function that is continuous over these intervals here and discontinuous everywhere else. So in other words, it's undefined for 0 and 1 in the denominator. So I believe that would work. Okay, total agreement with question 21. I think my function is valid, but yep, so just sort of analyzing continuity here. Be well.